we've been covering lately. Okay, so maybe I'll fire up OneNote and put out the outline of what we're going to cover today. Here's something that was covered after class last time. Let me just see if I can share that as a starting point. Okay, and then maybe advance the slide. Okay, so we've been doing different things. We've been solving for the steady state and stationary distribution when it exists by using this equation to find the stationary distribution. And if the process is irreducible and has positive recurrent states, then the pi that we find from this equation turns out to be the steady state. So we use this to first find the stationary distribution and also the steady state distribution. So we should be able to do this by hand when there aren't too many states, such as 2 or 3. And if we have, pardon me, if we have more than 2 or 3, then we also have an algorithm. To do the same thing for us on the calculator. Okay, so this is one bullet item, I suppose. The other items that we've been talking about are the forward and backward equations. So might as well write those down. P of t prime equals q times P of t are equal to P of t times q. And these are systems of linear differential equations. And we've had a little practice of doing this. We did this in the 2-state. So we went through this in the 2-state Markov chain, Markov process rather. So that's the one we did it, and we did it in general for that one. And then more recently, we've been doing a few examples. So we did this one. It's fairly simple. And then more recently, I've been talking about this one, where this is lambda. These are both examples of what are called pure birth processes. I think I even gave a homework the other day to do something that looked like this, where this was 1 and this was 2. So we have done some pure birth examples. If I were to put another one on the list, so I think we've talked about some of these in different situations. If I were to put another one on the list, it might be the continuation of this one. I'm not sure I'd want you to find everything though. Let me see, but if that has just lambda, 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 That's, these are, these, whoops. This one, and this one is what's called a pure birth process with constant rate up. And so, well, they get progressively harder because this has 4 entries in the PFT matrix. This has 9, and this one would have 16. Now, a lot of them would be 0 because you can't go downward, but there still would be some others to do. So if you were to do this one, what I would suggest is to do this. Just go, well, let me see. This is a little involved. It could be a homework problem, but it wouldn't be a test problem. So maybe I'll just stay with this one and take a check off this. I'd have to think more about what I'd want you to do here because it's a little involved. All right, that's the second bullet item. We've talked a little bit about each of these topics. Does anyone come in the meantime that needs permission to record? If so, please say something.
If I could, I would appreciate it.
Sure. Let me just get out of this if I can. Stop sharing. Well, wait, right here, I'm fine. So Candace, right?
Yes.
Yes, you have it.
Hey.
Alejandro, I don't remember you being here before, but I guess you have it. Maybe you were here. Is there anyone else who just came online? At the list, it looks like people are done. I think we're okay. Okay, so let's reshare. Get back to this bullet items that we're talking about. Okay. Well, of the two alternatives, solving a system of linear differential equations is easier than solving. Okay, yeah, solving a linear algebra problem. Yeah, so a system of not differential equations, a system of linear equations is easier to do than solving a system of linear differential equations. So this is more involved. And I guess along the way, we've solved, our techniques have been what? Our techniques so far have been separation of variables. And the other one was solving a linear differential equation that looked like this. F is the function we want, and G is a given function, alpha is a constant. So these are two techniques that we've already talked about, how to do separation of variables and how to solve this linear differential equation with constant coefficient. Something that we haven't dealt with too much is some of the theory, and some of the theory we should take care of because some of it is beyond the scope of what we want to prove, but we do want to use it. So let's do that today. Let's supplement what we've been doing with some of the theory. But any questions about these topics before we move on? We can do some of these maybe after class if anyone has any questions. I think I assigned this last time. Okay, let's look at some of the theoretic results. So there's a nice result here. Let me just lift it out of the book. Yeah, it's on page 103. And so let me just, I'm not going to prove it in either way, so at least I'll just compare it to what we've done in the past. So we had this result for chains. The Markov chains we have theorem 5 in chapter 2. And let me see if I can find a page. Yeah, page 64. So if you want to refer to it, it's something we did before the last midterm. It's on Markov chains. And on page 64, it says the following: an irreducible positive recurrent Markov chain and irreducible positive recurrent Markov chain has a unique stationary distribution pi given by one over mx, and this is for all x in the state space S, where m sub x was defined to be the expected time it took to go from x back to itself for the first time. Okay, so we've used this, we've seen it. It's a very nice theorem because it guarantees when you can have an irreducible Markov, when you can have a unique stationary distribution. That's the key. We want there to be a distribution and we want it to be unique. And this is telling us if we're irreducible, so all states communicate with each other. No recurrent states. So no recurrent states are ones where it took an infinite time to get back to itself for the first time. We don't have any of those. Then we can be assured that there's a unique stationary distribution that's given to be this. And then there's conditions later, theorem 7, that told us when it was actually steady state. But at this point, I just want to fix on stationary. Okay. One way we use this was to find mx. So we would find the stationary distribution back in chapter 2 by either by hand or by algorithm or some way or the other. And then once we knew it, we could then solve for mx, which is the average time it takes to go from one state back to the other. So this theorem goes over to theorem to chapter 3. Let me go back to where I was in chapter 3. Same theorem occurs. It looks a little different. Let's see where it is. Yeah, it's on page 103. And well, I'll say it out loud before I write it, and then I'll go from there. An irreducible positive recurrent process has a unique stationary distribution pi. Okay, and here they leave off the exception, which unless S consists of a single necessarily absorbent state is given by this. So this is on the bottom of page 103. So see that. See the bottom of page 103. Okay. They don't prove it and they don't actually state it as a theorem here like they did before, but it's okay. So basically, an irreducible, I'll state it, what they just said in the sentence, irreducible no way. Yeah, an irreducible positive recurrent Markov process has a unique stationary distribution pi. And I'm going to leave off the exceptional case. They're talking about a strange case here where there's only one absorbing state. I'm going to not even make reference to that. I'll just say stationary distribution pi given by pi of x equals 1 over qx. And that's for all x in the state space S. Okay, so it's almost the same statement. Contrast this one with this one. What is mx? Mx is the same thing it was before. It's the expected time to go from a state x back to itself for the first time. So that's still as it was before. And the q of x is what you think it is. Well, I have to be careful. Q of x is a q value, but I have to be careful what q of x stands for here. I believe that q of x is minus q x. So let me make sure of that. So that may take a bit. Let me look back and make sure I got that right. Okay, I think I've got it down to the right page I need to look at. Yeah, so what I need is back on page 88. There's an equation 12 there that tells me that when x equals y, q of x is minus q. Yeah, so this is correct. So this is correct. And you sort of need both of these. Let's do an example of this one, since this is new. Let me see if I can just go back a little bit and pick out a nice example that we've worked before. So this was our algorithm. I think we did an example here. Let me go past this. No. Well, this is sort of a nasty one, but we did it. Okay. All right, I'm going to go look for a nicer one. This was sort of involved, but it is convenient. It's right in front of us, so it has something good about it. I'm going to go back a little bit further. And it would probably be after this. This will work. So we did this example. I don't seem to have, well, maybe I can go back one more page. Let me just see where I am. There we go. Okay, so here's a relatively simple Markov process. It's 3 states. It has rates that look like this. And in the past, we figured out what pi is. This is the solution of pi. So this is not too long ago. We used this equation and solved it by hand right here. And it turned out this was the answer. Now, if you look at the picture, the chain is irreducible because you can get from any state to any other state. And it will have no recurrent states because it's a finite state space. No recurrent states only happen when there's possibly happen when there's an infinite number of states. So this fits the theorem I just said. It's irreducible, it's positive recurrent. So what does it mean? It means that the theorem said, so this is the latest theorem, so this is an addendum. Oh, no good. Oh, that's frustrating. I lost my example. Ah, I can't win here. All right. Even worse, I can't get one note up. All right, let's try this one more time. Okay. All right. Okay, so I'm finally got my one note back. And I'm trying to recover where I was. And here's where I was. And this was our check. And okay, so let's use this page. But let me be careful now that I don't lose it again. So I'll shuffle my furniture around a little bit. Okay, so in this case, we had the stationary distribution was this. And what I was trying to illustrate was what we know. From today, we know that pi at any point x is 1 over mx times q of x, which we figured out was what? Minus q00. Okay, so how does this work? So let's do it when x equals 0. When x equals 0, we already solved for the stationary distribution by hand, and it was 3/13. So this would be 3/13. We know the whole thing. And we know what Q00 is. Q00 is minus 2, and if we negate it, we just get positive 2. So what this equation says is that 3/13 is really 1/2 m0. How did I do that? By recognizing that Q00 is -2. And if I negate it, which this says to do, I make it positive 2. And so I get this equation. And from this equation, it's not hard to solve. This implies that m0 would be what? M0 would be equal to 13/3 times 1/2, which is 13/6, which is 2 1/6. And that would be equal to m0. Make sure I did that right. Yeah, so 1 over m0 is 6/13. So m0 is 13/6. And that's 2.5 units of time. So on average, the time it takes to come back to 0 for the first time is 2.5 units. So if I ask you to find m0, the easiest way to find m0 is if you've already found the stationary distribution, which we have in this case. In this particular case, we already worked out what the stationary distribution was at 0. It was 3/13. So that gives you this equation here. And then it's simple to solve for this. Let's do the other two. What would, if we put in So in here, I put in x being 0. Now I'm putting in x equal 1. If I put in x equal 1, I get pi at 1. That would be 1 over minus q11 m of 1. And q11 can be found from the matrix. Q11 in this case is -3. So when you negate that, it just becomes positive 3 on the bottom. So this is 1 over 3m1. But on the other hand, pi of 1 from previous calculation was known to be 6/13. So if you set this equal to 6/13, you could invert this, getting 3m1, and that's equal to the reciprocal of this. And then you can just simply divide by 3 to get that m1 would be 13 over 18, which is a little less than 1. So here we have what m0 is, and here we have what m1 is. What is m1? It's the average time it takes to first get back from 1 to 1. It's shorter than the other one, but that makes sense. Why? Because there are more ways to get back to 1 from 1 than there were for 0. For 0, you have to go, there's only one way. You can leave, you have to come back this way. But from 1, you can leave and come back this way or this way. So it makes sense that this would be smaller than this one. To finish this out, what would happen when x is 2? When x is 2, you would get that pi of 2 by the theorem is 1 over q22 m2. q22 can be picked off from the matrix. q322 is -3 again. Yeah, I guess. And so this on the bottom would be 1/3. So this would become 1 over 3 m2. But pi 2 was something we already calculated, and that was 4/13 up here. And so if you want to flip this over, that's 13 over 4. That's equal to what you get when you flip this over, 3m2. So what does it all imply? It divided by 3. 13 over 3 times 4 is 12. A little bit bigger than 1 is the average time it takes to go from 2 back to 2. Okay, so this is not a hard calculation, and it's similar to what we've done before. Questions on the calculation? Okay. We had a nasty monster that I just found along the way with like 5 states. You could do it for that one as well. Why don't I ask you to do it for that one? So let me see if I can find it again. Any questions on this calculation? Because once I leave the page, it may be hard to get back to. Unless I keep track of where I'm at. But where am I? I am on something that says -3/6. After this, we did a harder one. Just want to see if we still have it. Nope. Yet. Algorithm, and after the algorithm, I think it's when I did. There it is. Okay, so homework. Take this down. Write down what Q is. Write down what the stationary distributions are. I think we did this in class using the algorithm. And now find all the average times it takes to go from each state back to itself for the first time. So find m0. M0, M1, M2, M3, and M4, which you should be able to do knowing what Q is and knowing what the unique stationary distribution is. I'll give you another little time to copy this down. Okay, the advantage of this homework problem, now there's a disadvantage and an advantage. The advantage is this problem we did. So for this diagram and this Q matrix, which corresponds to it, we already found the stationary distribution using our algorithm. And it turned out to be this. So write those down. Otherwise, you need to do it again, which probably wouldn't be bad practice anyway, but if you've done it once, you probably don't want to do it again. Okay, and then from everything here, find the M sub zeros, or the M0, M1, M2, M3, and M4. Are we good? Okay, so now let's go back to where we were. Current stuff. Maybe not. Okay, here we go. So where are we so far today? So here's our summary. Here's our new result, how to find the M's using this theorem on page 103. Very well, which is very similar to the theorem we already did in chapter 2 on page 64. The only thing that you needed to know is that QX is minus QXX. So it's the diagonal element. And don't forget the negative sign. If you forget the negative sign, you're going to get what? You're going to get negative averages, and that just doesn't make sense. Okay. All right. What else can we do now? Well, one result that we haven't done and we haven't talked about for processes yet is, suppose we don't have just a finite number of states. I mean, these examples have either 2, 3, or 4 states. The example we just assigned for homework had like 5 states. But we've seen in chapter 2 and 1, as far as that goes, that there are Markov chains that have infinite number of states. So let's turn our attention to a Markov process that has an infinite number of states. So I'll flip the page. The obvious, well, I guess there are 2 obvious ones. Yeah, let's turn the page. Edit page. So if we're going to imitate what we did in chapter 2, and so this title of this would be Markov processes that have an infinite number of states. So recall what we did before. Recall in chapter 1 and 2, we had 2 particular types that we studied. We studied the birth disaster type, also called the birth catastrophe type. And we studied the birth death chain. And we did a lot of stuff with both of those in chapter 2. A lot of stuff means what? Oh, we figured out in chapter 1 as well for some, both of them, when they were recurrent, when they were transient, etc. We also found their stationary distributions and even more, but let's see if we can do some of that stuff. The birth disaster was easier, so if I wanted to go from an ease point of view, probably I should do that. But in terms of what's more commonly used, it's the birth-death chain. And that's spelled out a little more in the book. So let me go with that one, at least initially. I don't have time today to do both, but I'll do this one. So how would this thing look? It would look like what could follow. We have 0 and 1 and 2 and 3 and so on. And we already know how a birth-death chain looks in terms of transitions. It looks like this. And we're allowing the possibility of going on infinitely many. And when we did this before, we in chains, we called this P0, P1, P2, etc. And the probabilities going down, we call Qs. What's commonly done for this one is to call this one lambda 0, this one lambda 1, lambda 2, lambda 3, and so forth. And to call the ones going down mu's, mu1, mu2. They're indexed by where you're coming from. So you're coming from 2, going to 1, mu3, mu4, and mu5, and continued. Now, again, with Markov processes, we customarily don't show the return rates. They are there, but we usually don't show them. Okay, so this would be how a birth-death process looks. And these lambdas and mu's are rates. So what can we say about the rates? The rates that are shown, the lambda I and the mu I, are greater than or equal to 0. What do we really need in order to do very much with the Markov process? We need the counterpart of the one-step transition probability. And the counterpart of that is the Q matrix. Okay, so let's write down the Q matrix. Apparently, I'm not allowed to scroll down unless I fool it into doing it. Okay. So what does Q look like? Q looks like, well, it's an infinite matrix to begin with. And let's go with what we know. The rate of going from 0 to 1 is lambda 0, so that would be here. But in an instant of time, you can't go to 2. There's no arrow going directly there, so that would be 0. Nor can you go to 3 or any higher state. So there's zeros all the way out this way. And then the first entry, it would be the loop, and we already know how to figure that out because the rows of the Q matrix must sum to 0. So this would be minus lambda 0. Okay, that's row 1. What does row 2 look like? Well, 2, we're going from 1 to places. If we're going from 1 to 0, that would have rate mu1. And then if we're going from 1 to 2, that would be have rate lambda 1. And 1 to anywhere else has no arrows, so those are all gone. And the rate going from 1 back to itself would have to be such that this row adds up to 0, so it would be minus 1 plus mu1. All right, that's a start. Maybe I'll do 1 or perhaps 2 more rows, just to make sure we're all together how this thing looks. What about from 2? Well, from 2, there's no way to get to 0 in instant time, so that's 0. But from 2 to 1, there's a rate, which is mu2. And from 2 to 3, there's a rate which is lambda 2. But there's no way to get from 2 to 4 or any higher state in one instant of time. So these are zeros the rest of the way. And then this would have to be such so that this row adds up to 0. So it would be minus the sum of these, lambda 2 plus lambda mu1. Okay, and this got lost in the shuffle. So this was minus lambda 0. Okay, so this is the pattern. Without going through the explanation, how would the next row look? We would have 2 zeros. We would have a mu3 here, a minus lambda 3 plus mu3 here, and a lambda 3 here, and then 0 the rest of the ways. And the rows keep coming like this, and so do the columns. And that's the Q matrix. Any question how I got the Q matrix? Cool. Let's see if we can find. So I'm assuming by the fact that I've got all these zeros in the diagram that all these rates are positive, right? If the rates were actually 0, then we wouldn't be able to get around. It wouldn't be reducible. And so we don't want to assume that. So I'm assuming all these rates, well, actually, so greater than equal to 0. Let's go further. Let's just make it strict. Okay, so this is true for all y. The rates, lambdas and mu's are all strictly positive. Okay. Well, now that you've got the birth-death, infinite birth-death chain in front of you, whoops, infinite birth-death process, sorry, process when you have continuous time in front of you, and you have its Q matrix, there's a choice of what to do. The choice is either solve the forward or backward equation, which looks highly, well, it's very, very difficult to do, if not impossible. So what's the simpler task? How about the steady state or stationary distribution? Okay, so let's try that with this slight little time we have. To find the stationary, what do we need to do? We need to do pi times q equals what? The 0 vector? That's the equation to find the stationary distribution in the simple cases that we've done, but it's also the same equation that would work in this case. Let's see if we can do it. I'm trying to see if there's anything we've got to worry about here. Maybe, but let's just try. let's give it a shot without worrying too much about it. So let me move this. Yeah, I'm trying to avoid losing my picture. Sure, that's going to work. Okay. So what is pi 0 or pi? Pi would have pi 0. Well, I keep losing that already. I don't want to lose this picture. Pi 0, pi 1, pi 2, etc. The algorithm will not work here. It's an infinite dimensional matrix, so we have to start it by hand and look for some patterns. And I'm losing stuff, so I'm a little concerned. Okay, so that's how pi looks. So what we need to envision is, I can't keep the first entry here. All right. So here, I'll start us off. So pi 0, comma pi 1, comma pi 2, comma pi 3. Continues forever. And multiply it by the Q matrix. Q matrix has minus lambda here, minus lambda 0 mu1. Then it has lambda 0 here, 0 the rest of the way. And it has minus lambda 1 plus mu1 here, lambda 1 here, and 0 the rest of the way. And maybe one more row just to get us rolling. 0, 2, minus lambda 2. Minus it's in front of everything, lambda 2 plus mu2, and lambda 2. My rows are misaligned. Okay, so let's go down and see what we can do. And this product is equaling all zeros, so that's the good part. When you first multiply this vector times this matrix, you will get minus lambda 0 times pi 0 plus pi 1 times mu1. And then there are zeros the rest of the way in this column. So there's nothing, all the further multiplications are 0. And when you do all of this, you will get 0. Okay. From here, we can solve for pi 1 in terms of pi 0. So let's do that. So what can we say? We can say that bringing this to the other side, lambda 0 pi 0 is equal to mu1 pi 1. And then we can just divide by mu1. Remember the lambdas and mu's are all positive numbers, so there's no zeros there. So what do we get? We have pi 1 is lambda 0 over mu1 times pi 0. Box it. Keep it. We're good? That's just from the first multiplication of this infinite pi vector times the first column of what? Of the Q matrix here. Okay, let's move on. Let's multiply the next one together. Well, it already got lost here. This term here was what? Lambda 1 plus mu1 with a minus in front of it. Okay, so what happens when you now multiply this vector times the second column? You will get lambda 0 times pi 0 again. And you will get pi 1 times this. So that's minus lambda 1 mu1 times pi 1. And you will get pi 2 times mu2. That's pi 2 parentheses. And all of that is equal to 0 because over here everything is 0. Okay, so hopefully you all track what I'm doing. I'm multiplying this infinite pi vector times the second column. The second column looks like this. Now I should say after this, the next row down, I guess if we scroll up, we can see it a little better. So in the second column after the third row, so from here onward, it's 0. So there are no more terms to consider for this product. That is over here, the next entry down would be 0, 0, and it would continue zeros as that's happening in the first column as well. Okay. So what can we do here? We can do two things. We can, first of all, realize that we already know what pi1 is in terms of pi0, so we can substitute that into here. So we have 0 is equal to lambda 0 pi0 minus lambda 1 plus mu1 times pi1, but pi1 is equal to this stuff. So substitute that in there, lambda 0 mu1 pi0. And then we have the third term here, which is mu2 pi2. So I'm just taking this equation and substituting what we already found out, that pi1 is in terms of pi0. Let's make sure I did that right. I think so. So this looks okay. Now what we can do is concentrate on the first two terms of this. And what we see is that both of the terms in here have a constant term of pi0. So we can rewrite this equation as something times pi0 plus mu2 times pi2. Okay, now what's left in here? What's left in here is lambda 0 plus, or minus, I guess, lambda 1 plus mu1, and lambda 0 mu1. Okay. And you can recover the original just by multiplying through. Pi0 times lambda 0 is this, and all of this stuff times pi0 will give you this. Okay, let's simplify what's in the parentheses. Maybe get a common denominator, which looks like it would be mu1. So we multiply top and bottom here by mu1. We have lambda 0 mu1, and the bottom is mu1. And then we're subtracting off lambda 1 plus mu1, parentheses lambda 0 over mu1. All of that times pi0. This is a little bit of algebra. Okay, but we're getting there. When you subtract the fractions, notice that we have lambda 0 mu1 here over mu1, but we also have lambda 0 mu1 here over mu1, and it comes with a minus, so that those two nicely cancel. And so what's left is just, so I'm saying this cancels. Oh goodness, shouldn't have even tried. Let me see. Let me see if I can just get back to where I was. Okay, so I'm going to say this circle instead of 10. That agrees with the second part here, lambda 0 mu1 over mu1, and that comes with a minus. So that cancels this part. So what survives? What survives in this square bracket would be lambda 0, lambda 1 with a negative, all over mu1. That's this times this over that, times pi0 plus mu2 pi2. Okay. But from this equation, we can see that we can solve for pi2 in terms of pi0. So let's do that. If we just bring the first term to the other side, we'll have lambda 0, lambda 1, all over mu1. So all of that times pi0, I suppose. And on the right side, we just have mu2 pi2. And what comes natural is to divide both sides by mu2. So you have lambda 0, lambda 1 over mu1, mu2, pi0, and that equals pi2. and save that. Okay, so where are we at? We have almost no time left. Essentially done, but it's okay because we're pretty much where we want to be. We have two equations now. We have pi 1 in terms of pi 0, which is boxed up here. And then we have this one. Let's write this one right underneath it. So the one that we just did looks like pi 2. And if you look at it again, it's lambda 0, lambda 1. Lambda 0, lambda 1. All over, what is it, mu1, mu2? Yes, mu1, mu2 times pi 0. Okay, so the good news is pi 1 is in terms of pi 0, pi 2 is in terms of pi 0. And I think you can believe a pattern. Let's do the pattern for pi 3. Pi 3 looks like it would be, from what we've done so far, lambda 0, lambda 1, lambda 2, all over what? Mu1, mu2, mu3 times what? Pi 0. Okay, that's a guess, an educated guess, based on the patterns of pi 1 and pi 2. Looks like pi 3 would have one more factor of lambda in it and one more factor of mu in it times pi 0. If you wish, you are welcome to check that. Okay, it's not any different than what we've already done. What you have to do is multiply this infinite pi vector times the third column and set it equal to 0, and then solve for pi 3. And if you do that, you will get this. So let's go the whole way. What do you think pi n looks like? If the pattern persists, it should be lambda 0, lambda 1, lambda 2, all the way up to lambda n minus 1. And on the bottom, it should be mu1, mu2, all the way up to mu(n). If you take all of that and multiply it by pi 0, you should get pi n, where n is greater than or equal to 0, right? Well, I guess we got to be careful. Greater than or equal to 1. That's really what we've done. So we're saying the same pattern persists. Okay, so good news. All the pi's are in terms of pi 0, but don't forget, we're looking for a distribution. So the end of this comes soon, but remember what? Pi 0 plus pi 1 plus pi 2 plus pi 3, etc. adds up to 1. It's a distribution. Okay, so now if you put all,
Is it important?
say it again, please. I'm not sure I heard whatever the question was there. Maybe it wasn't for me. Okay, so let's finish this. So pi 0 is what it is. But pi 1, we can just lift from our box formula. That's lambda 0 over mu1. Lambda 0 over mu1 times pi 0. And what was pi 2? Oh, lambda 0, lambda 1 over what? Mu1, mu2? Pi 0. What was lambda 3? Lambda 0, lambda 1, lambda 2, all over what? Mu1, mu2, mu3 times pi 0. Off we go. And that all sums to 1. But each term in this infinite series has pi 0 as a factor. So factor out the pi 0s. So pi 0 times 1 plus lambda 0 over mu 1 plus lambda 0, lambda 1 over mu 1, mu 2 plus lambda 0, lambda 1, lambda 2 all over mu 1, mu 2, mu 3. Keep going. All of that equals 1. So, conclusion, pi 0 would be 1 all of this stuff, solve for pi 0. So it's 1 over what's in the parentheses here. 1 plus lambda 0, mu 1 plus lambda 0, lambda 1 over mu 1, 2 plus lambda 0, lambda 1, lambda 2 all over mu 1, mu 2, mu 3. It's an infinite series. So this is what pi 0 is. But once you know pi 0, you can go back here and get all the others. Pi 1 is just pi 0 times this quantity. My mouse would work. Yeah, pi 1 is pi lambda 0 mu 1 over pi 0. Pi 2 is this times that. So in general, what should pi n be? Pi n, well, it should be this. And now we know what pi 0 is. So what is the final conclusion? Final conclusion is this is pi 0, but we know a little more. And pi n equals the same denominator. And what goes on top is one of these guys. And if you're doing pi n, I think it's the one, well, I shouldn't think, I should just go look. It's this one. So it ends on n on the bottom and n minus 1 on top. So the one that's on top looks like lambda 0, lambda 1, all the way to lambda n minus 1, all over mu 1, mu 2, all the way to mu n. So that's the formula for pi n, where n is what? 1 or more. So, cool. We've done this before. We did something similar to this for the chain back in chapter 2. And we actually had things that looked similar to this. It was ratios of p's over q's. This time it's ratios of lambdas over mu's. And I'm out of time, so I'll just let it go with this. Will this always give us the right formula? Well, the answer is yes and no, as long as you recognize what the conditions have to be. This is a series, an infinite series of positive terms, because we assumed all the lambdas and mu's were positive numbers. That infinite series of positive terms has only two possibilities. It either converges or it doesn't. If it doesn't converge, then it goes to infinity because it's not oscillating. There's no negatives in it at all. Let's think about the second case. Suppose it goes to infinity. If it goes to infinity, then pi 0 looks like 0, because 1 over infinity looks like 0. But if pi 0 is 0, all the other pi's are in terms of something times pi 0, right? So if this guy up here, if pi 0 is 0, then when you multiply through, you're getting all the other ones to be 0. So it won't always have a steady state. It's only going to have a steady state when this infinite series converges. If it diverges off to infinity, then there is no steady state. Good place for me to stop. Yeah, I'll take a little water break, come back and talk about other things, this included. And oh, for your information, this is in the book. Where? Good question. It's toward the last part of the chapter, I think. Yeah, it's on page 104, 105. The derivation is there. So what I would say is read, let's see. Hopefully what I did in class made some sense, but if not, read pages 104, 105. And future homework. I'm trying to see where they have it. Okay, oh, I'm in the wrong place. Would be number 16 and 17 and 18. So look at problem 16, 17 and 18 at the back of the chapter. Okay, I'll see you right after I take some water. A little longer, I have to go get some water. Okay, I'm back. Any questions about, well, let's start with what I've been talking about here, what we did today. What did we do today? We found a formula for the stationary distribution of a birth-death process. And not only that, we didn't have time at the end, but we also have conditions when it has when a birth-death process, infinite states, when it has a stationary. The condition we require is pi zero has to make sense, which means this series on the bottom has to converge. If it doesn't, then pi zero will be zero, and so will all the other ones, and they won't add up to one, so it won't be a stationary distribution. That's one thing we did today. What was the other thing? The other thing we did today was the theorem saying that how does pi zero look? It looks like when it exists, it looks like the following. 1 over minus q xx mx. So if you have a stationary positive recurrent uh, positive recurrent chain, that means there is the unique stationary, and then you could actually find pi x in terms of these two quantities, qxx and mx. And we worked an example of that type too. So that's what we did today. Questions on either of those things? I mean, it's easier to talk about what we did, I suppose. I'm looking at my picture and some of it got erased as usual. What about the first column here? Yeah, that got erased too. We're from 2, this was mu1. And this one was what? 0, I think. Yeah. Anyway. If there are no questions, I'll say just a word or two more about this. So the two theorems say what? The one theorem says if the chain, try it again, if the process is what? Irreducible and positive recurrent, then there's a unique stationary distribution and it looks like this. Now, we didn't prove that, and we're not going to, but it doesn't mean we can't think about it, what it's saying. It's saying that if we have an irreducible positive recurrent chain, then there's a unique stationary, and you can actually interpret it to look like this. Now, from what I just said, this birth-death chain might have a unique stationary and it might not. When does it not have a unique stationary? It does not have a unique stationary distribution when this infinite series sums to infinity. Because if it sums to infinity, then pi 0 would be 0. And because all the other pi's are in terms of pi 0, multiplying pi 0 by some constants, then all the others would be 0 as well. And they can't all add up to 1 if they're all 0. So what must that mean? When this series actually goes to infinity, that must correspond to not being positive recurrent, right? Because if it were positive recurrent, then we know by the theorem there's a unique stationary. But we know by the form here that there is no stationary. So what we're coming away with is if this infinite series diverges, goes to infinity, then what? Then either, and well, yeah, let's write that down. Let's just write that down. So here's a remark that follows all this work. If 1 plus lambda over mu1 plus lambda 0, lambda 1 over mu1, mu2, lambda 0, lambda 1, lambda 2 over mu1, mu2, mu3, etc. If that infinite series is infinite, then this Markov chain, process. Got to catch me on that. It's so easy to call it a chain when it's a process. Then this Markov process is not positive recurrent Okay. So it's not positive recurrent when, if, and this is an if and only if it says then, but I should have said if and only if. That's a little bit stronger remark. If and only if. Okay. And how do we know that? Well, again, if the infinite series goes to infinity, then we already saw there is no unique stationary distribution. There's a unique stationary distribution, we solved for it. And in the case that this infinite series diverges, all the pi's turn out to be zero, which means it can't be a distribution. So there is not a unique stationary distribution. So by the theorem that we said over here, this cannot hold. It only holds in the case that, that, that it's irreducible and positive recurrent. So since this doesn't hold and it's pretty clear it's irreducible, the thing that's is it's not positive recurrent. Now,
laughs a lot, but he laughs loud, and frankly, it's infectious.
you got some background noise. Yeah, thank you. You might want to lower. Any questions on what this remark is saying? So you can tell if it's not positive recurrent, then what's left? Then it's either no recurrent or transient. Okay, so those are the only possibilities, because as before, all states are either transient or recurrent. And just like before, the recurrent ones are either what? No recurrent or positive recurrent. So if the chain, if the process is birth, death, irreducible, and positive recurrent, then we know there exists one stationary distribution that looks like this. But in the case we just have here, if this infinite series diverges, then it doesn't have a unique stationary distribution, which means we're either in the transient or no recurrent state. If you ask me which one, then we'd have to do a little more work to be able to tell which one we're in. But we're not in the positive recurrent if this infinite series goes to infinity. If the infinite series converges, then we're in the positive recurrent state. Why? Because if it converges, everything we did makes sense, and that's a stationary distribution. And that can only happen if the chain is irreducible and positive recurrent. So what I could say is, let's do an example real quick. Let's do an example where the lambdas are less than the mu's. So let's call the lambdas 1. All the lambdas are the same. And let's call all the mu's 2. If you have that example, what happens to the series? So take a look at it. It's 1. Lambda 0 over mu1 would be 1 over 2. This would be 1 over 2 times 1 over 2, which would be 1 over 2 squared. This would be 1 over 2 cubed, and so forth. So if the rate of going down, or the death rate, I suppose, is less than the birth rate, greater than the birth rate, then this is a geometric series, and this actually sums to what? 2, I think. It's 1 over 1 minus a half, which is 2. Yeah, which is finite. So in that case, there's a birth death, and there's a stationary distribution. What does it look like? Pi 0 pi 0 looks like 1 over the series, which is 1/2. Pi 1 would look like 1/2 times 1/2, so it would be 1/4. Pi 2 would be 1/8, and so forth. So in this case, if the death rate is faster than the birth rate, then there's a stationary and a steady state distribution. Okay. On the other hand, if you have these rates reversed, so this is example 1, example 2, if lambda was equal to 2 and mu was equal to 1, so the birth rate was faster than the death rate, then the series would have, well, then what do all these things look? The lambdas are 2s and the 1s are in the bottom, so you'd have something that looks like 1 plus 2 plus 2 squared plus 2 cubed, etc. And that goes off to infinity. So in that case, there is no stationary distribution. And so that should make some sense, because if the birth rates are bigger than the death rates, after a long period of time, you'd expect to be, just having ever more people, because the birth rates are exceeding the death rates. Or if I want to make it more topical, I could say if the rate of catching COVID is twice the rate of not catching it, or something like that, then you'll have a lot more cases and it'll explode. Okay, now the interesting case would be, suppose the rates are the same. So that would be example 3. If lambda is equal to 1 and mu equals the same thing, then what is this infinite series doing? It's 1 plus 1 plus 1 plus 1. So the infinite series is going up to infinity. So once again, there's no stationary or distribution. If there's no stationary, then there's no steady state. So if the rates are equal, this thing is still exploding. It looks a lot like what we did in chapter 2 with birth death chains. So if you sort of go back and look at that, you'll see that this is a very similar result. And I might use that similarity next time to get some of the other results. So the other results we had back in chapter 2, in chapter 2, we were able to tell whether it was transient, recurrent, or positive, no recurrent or positive recurrent. So far for processes, all we've shown is if this infinite series diverges, then it's not positive recurrent. That's all we've shown for processes, but we have more information that we could draw upon from chapter 2, which we could do next time. Questions? This would be a formula to memorize for the upcoming final. So I could easily give you an infinite birth death process and ask you to find its stationary distribution. And like chapter 2, it's going to require you to go back and remember some stuff about infinite series from calculus. Because in order to nail down what the stationary distribution is, I mean, examples I just gave here, this was geometric, so you could recognize it. This was also geometric, so you could recognize it. This is, I suppose it's geometric, but you're just multiplying by 1 each time. But in general, you want to be able to recognize whether an infinite series like this converges or not, and that's calculus. So you should go back and look at some of that stuff. We've done that already in chapter 2. So that's not a new application of calculus, but it's coming up again for processes, just like it did for chains. Questions, requests? I can look at some of the future homework if you like. I can look at some of the old homework. You're very quiet today, so I'm not sure what you want. Let me look at one of the homework problems just for the sake of talking a little more, hopefully helping you. So what did I suggest? I suggest 16, 17, and 18. So I'm looking at 16. 16 says, consider a birth-death process on the non-negative integers whose death rates are given this way. Determine whether the process is transient, now recurrent, or positive recurrent if the birth rates are given this way. Okay, well, I don't know if we have everything we need to do that, but I think we could do something. Let me turn the page. We will need to make reference to this stuff, though. So remember that there's a stationary if and only if this series, well, if it converges, then there's a stationary one. And if not, then it's not positive recurrent. So I'll flip the page. Put some lines on it again, if I can. I don't think I can. Okay, so try it again. Yes. All right, so we're looking at 16. And we're talking about something on the non-negative integers, so that's exactly what we're talking about. And they tell us that mu of x is just x. So mu of 1 would be 1. Mu of 2 would be 2. Mu of 3 would be 3. Mu of 4 would be 4, and so forth. And what are the birth rates? Well, there's two conditions. Condition A has us assume that lambda x is what? X plus 1. Okay, and that's for x greater than or equal to 0. So when x is 0, lambda 0 would be 1. When x is 1, lambda 1 would be 2. Is that correct? I think so. When x is 2, lambda 2 would be 3. So I think the first case that we're looking at is this. Make sure I have it right. Lambda x is x plus 1. We'll be putting 0, lambda 0 would be 1, putting 1, lambda 1 would be 2. Yeah, I think it's fine. Okay. So that's how this looks. And they want us to know whether Okay, they want a little more than I've covered in class yet. They want to know, is it transient? Is it positive recurrent? Is it no recurrent? Now, the part that we've done in class is we can look and see if it has a stationary distribution. If it has a stationary distribution, what do we have to look at? We have to look at 1 plus lambda over mu1, right? Plus lambda 0, lambda 1 over mu1, mu2. We have to look at this infinite series. Okay, so let's do that. Lambda 0 is 1 and mu1 is 1. So this is 1 plus 1. This is 1, and then lambda 1 is 2, and mu2 is 2. So that's another 1. And I think this is the case we sort of covered in class. Let's make sure. Lambda 2 over mu3, that's 3 over 3, and so forth. So it looks like this infinite series is this guy, which diverges. Okay, so what does that mean? It doesn't have a unique stationary distribution. So we're not in this class. We're either in the transient state or we're in the no recurrent state, but we're not in the positive recurrent state. Because if we were, then this series would converge. So it's not positive recurrent because this goes to infinity. So it's not here. And what do I think? I think it's probably transient. Because the rate going up, well, let me think about it. Rate going up is the same as rate going down. So maybe that's like flipping a coin. So I'm not sure. I think it probably is no recurrent, but it doesn't matter as far as having stationary, it doesn't have it. So at this point, we don't know whether it's this or this. Let's see if we can go a little bit past what I did in class so we can solve the whole problem. And so to do that, you probably have to look in the book for when it's transient and when it's no recurrent. Okay, so I didn't cover it yet. It's actually on the same page that I was. So if I had more time, I guess I probably could have gotten to it. It's on the bottom of page 105. So let's just look at it so we can use it at least. The bottom of 105 says, in summary, an irreducible birth-death chain is transient if and only if equation 51 holds. Equation 51 is this one. Okay, now that's different than what we've got. That looks a little bit more like what we did in chapter 2. So I'll just write what they have. They're summarizing something, but we haven't actually gone through the derivation. Here's just the summary. The summary is, if you've got this series with mu's on top and lambdas on the bottom, which is the opposite of what we got today. But if you look at the infinite series from x = 1 to infinity here, if this is less than infinite, then this holds if and only if something. Okay. If and only if the birth-death process is transient. Birth-death process is transient. Okay. And okay, so let's see. I think that's the key thing. We need to complete 16. So what would it look like in this case? Well, remember, let's see. Let's make sure we got this right. So how does this look like? When you start with 1, you would have what? Just mu1 over lambda 1. And when x is 2, it would be mu1, mu2 over lambda 1, lambda 2, and so forth. Okay, but mu1 is 1. And lambda 1 is 2. So this thing is 1/2. And so mu1 over lambda 1 is 1/2. What is mu2? mu2 is 2. And lambda 2 is 3. So that looks like 1/2 times, what did I just say? 2 over 3. And what would the next one be? The pattern is beginning to look like the harmonic series. 1/2, 2/3. And if I do mu3 over lambda 3, mu3 is 3 and lambda 3 is 4. So that's 3 over 4. And now it's become even clearer. So this is 1/2, 1/3, and 1/4. So this is the harmonic series, which does what? It goes to infinity. So since this is infinite, well, it's finite if and only if it's transient. So since it's going to infinity, then it's not transient. Okay, so this case is not transient by this condition. So it's not transient. But we already agreed it was not positive recurrence. So it's not this, and it's not this. What's left is this. So this is an example of a null recurrent birth-death process. And the thing that we didn't have before was this. I didn't get to this in class. And as far let me see how to get this from 18 in this chapter and the results in section 1.7. Section 1.7 is back in chapter 1. So they're going way back into chapter 1 to get this. So I'll look at that next time. But at this point, this got erased, unfortunately. But it was a summation of things that looked like the mu's were all upstairs, right? So things were inverted. Okay, so this is the thing I didn't get to in class, but if we just use it, this infinite series is a harmonic part of the harmonic series. It goes to infinity, and therefore this is not true, which means this is not true, so it's not transient. We already knew it was not positive recurrent because this thing diverged. So it must be null recurrent. So that's interesting. Here's an example of a birth-death process that's null recurrent. What does it mean? If all the states are recurrent, you will come back to every state with probability 1. However, the time on average, the average time it takes the first return is infinitely often. So that's always counterintuitive. Question on part A. Let's look at B. So for part B, they changed the example, right? So for part B, and where are we? Back in 16, they made lambda x be x plus 2. Okay. So if lambda x is x plus 2, and I assume therefore that the death rates haven't changed, they're still x. Okay. So let's draw the picture one more time. The death rates are still the same. So we have 0, 1, and 2, and 3, and so forth. And these are like what? 1, and 2, and 3, and 4, 5, and so forth. And that's the way that's because of what they gave us to begin with. But now the birth rates are lambda x, and the x is x plus 2 this time instead of x plus 1. Okay, so when you're at 0, your birth rate is 2. When you're at 1, your birth rate is 3. When you're at 2, your birth rate is 4. And so we get the idea. Okay, so that's the thing we're looking at in this case. Intuitively, it looks to me like if this is a population, it looks like it's growing faster than it's dying because the rates going up are bigger than the rates going down. So what would that lead me to believe? It would lead me to believe that it won't have a steady state. And I'm not sure if it's even recurrent. It might just be transient. But I don't think it'll have a steady state or stationary, and it may not even be recurrent at all. The last one was no recurrent. Well, let's see what this one is. So to do what we did in class, we looked at what? It's up there somewhere. It's here, this series. So we looked at 1 plus lambda 0 over mu1 plus lambda 0, lambda 1 over mu1, mu2, and so on. So this would be 1 plus 2 for this, all over mu1, which is 1. And now this one would be 2 over 1, and lambda 1 over mu2 would be 3 over 2. And the next one would be 2 over 1, 3 over 2, and then what? 4 over 3. And one more should be clear enough to tell us what's going on. And the next one is 5 over 4. Okay, so if we look at this series, it looks like what? It looks like 1 and 2 and 3 and 4. I'm going to make a mistake here. Let's see. 3 over 2, 4 over 3, 5 over 4 should have been. Anyway, the 2's cancel, the 3's cancel, the 4's cancel, the 5, and so forth. So it's pretty clear this goes to infinity. So this means what? No stationary distribution, which means we're either in the transient case or the no recurrent case. We're not in the positive recurrence case. We're not. Sorry. Let me try again. Okay, it came back pretty nicely. Let's see if I can just share it. Okay, so hopefully you can still see it. And this goes to infinity, which means it's not positive recurrent. So I put positive recurrent as a possibility. Positive recurrent, null recurrent, or transient. It's not this. Why? Because if it were positive recurrent, there would be a unique stationary distribution. This series would sum to a finite number, and it doesn't. So it's not positive recurrent. And now we just have to decide if it's transient or null recurrent. I think it's transient. To do that, we need to do this sum again. So we have to look at U1 over lambda 1. What is it? Yeah, U1, U2 over lambda 1, lambda 2, etc. U1, U2, U3 over lambda 1, lambda 2, lambda 3. Okay, so U1 is 1, lambda 1 is 3. So this is 1/3. Make sure I got that right. U1 is 1. I'm looking at my diagram. Lambda 1 is 3. That's correct. What's going on in the next term? This is 1/3. Now we have U2, which is 2, all over lambda 2, which is 4. And the next one would be 1/3, 2/4. And what's next? U3, which is 3 over lambda 3, which is 5. Okay, so again, looks harmonic. 1/3 here. These cancel 1/4 here. These, let me see. I gotta be careful. U1 was 1/3, so that's fine. The next one was, sorry, 1/3, 2/4, and what? 3/5. So this is not harmonic. What is it? This is 1/6, right? Okay, so it looks like the 2 can cancel, so it's 1/3 times 2 plus here. The 3's would cancel. And you get what? 1/4 times 5. Okay, so I take it back. It's not the harmonic series. It's something looking like this. Let me make sure. 1/3, 2/4, 3/5. The 3's cancel. And you do have 1/that. Let's just do one more for the good luck's sake. So the next one would be 1/3, 2/4, 3/5, and 4/6, right? So with all of this, what does this give us? The 4's cancel here, the 3's cancel here. And it looks like I have 2/5/6. I'm not sure about that. Yeah, I think I'm doing this wrong somehow.
Professor,
Uh,
isn't it 1/2 times 5?
1/2 times 5. Where are you?
For the third part where you have 1/3 plus 1/3 times 2 plus 1 over 4 times
Are you right here?
below it.
Oh, below it here?
Yes.
Let's see. So it looks like, let me double check. It was 1/3, 2/4, 3/5. So it's, yeah, the threes would cancel, and so you would have 1 over 2 times 5. Is that what you're saying?
Yes.
I agree with you. I think I wanted it to be this. Okay. So it's this. Okay. All right. So knowing that for this, the next one will do 1 over 2 times 5, and then we just have to multiply by what? Is it 4/6? If we do that, what do we have? We have a 2 up here, and this becomes what? 1 over 3 times 5? Oops, that
Would
one.
this series become like a telescoping series?
No, I'm not sure what it is. So let's see, a third. Okay, I'm assuming I'm doing this right. If I'm doing it right, I've got 1/3 for the first one. I've got 1/3 times 1/2 for this. I've got 1 over 2 times 5 for this. And if I did this right, I'm getting 1 over what, 3 times 5? I think that's right. Is that correct? If that's correct, let me know. So far, now the question is, what does that converge or not? Well, I'm not even sure I see the pattern to it. It looks like each of these have a third, and then and then each of these have a fifth, and it's going to 3. What would you guess the next 2 terms are? Well, okay, we know, I guess that we can help get that. So this term is 1 over 3 times 5. And then we'd have to multiply by what the next one is, which is what? So we've done 1, 2, 3, 4. My problem is I'm not sure of the pattern yet. Hmm. And the remark about the telescoping series, I'm not sure I see that either. So we want to see a little more? I'll listen. My problem is I don't recognize the series offhand. Would it be clearer if I just actually wrote it out? I don't know. So I've got a third. I've got a 6th. I've got a 10th. I've got a 15th. Oh, okay. Well, that does help me a little bit. Those numbers I recognize finally. Okay. I think. If you add 1 to 2, you get 3. And if you add 1 to 2 to 3, you get 6. And if you add 1 to 2 to 3 to 4, you get 10. And if I add 1 to 2 to 3 to 4 to 5, I get 15. So it looks like the denominator is the sum of the integers. And we know how to sum them. We know that in general, if you wanted to sum the integers, 1, 2, up to what, n? That would be n times n plus 1 over 2. That's a well-known formula. So what am I suggesting? I'm suggesting this looks like 1 over the sum of the integers. Does that help me? Let me think about it. Maybe. So let's write this one. So the 1/3 we can now write as what? Using this, it would be 2 times 3 over 2, which is what we had here. So, but maybe it's easier to write it that way. So the reciprocal of this would be 2 over 2 times 3, which is the 1/3. That's fine. What about the 1/6? The 1/6 would be the reciprocal of this. And what is this? This is 3 times 4 over 2. So that would be 2 over 3 times 4. And that's going to help. This one would be what? 4 times 5 over 2. So the 1/10 there is really 2 over 4, 4 times 5. And the last one, 1/15, is really what? 5 times 6 over, this is 15, right? Yeah. 5 times 6 over 2, which is 15, which would be what? 2 times 5 plus 6. Okay, so these numbers really look like 2 over 2 times 3 plus 2 over 3 times 4 plus what? 2 over 4 times 5 plus 2 over 5 times 6. So you can factor out the 2 and just worry about this stuff. And we've seen this before. This is a product. And yeah, in here, we end up eventually with a telescoping series. So that remark does appear to be on mark. And so what you're really doing is you're summing something that looks like 2 times the sum of 1 over n times n plus 1, where n could be thought of as starting from 2 on. Okay, so that's what you're trying to sum. And what we've done with this in the past is you can use a partial fraction decomposition. So 1 over n plus 1 could be written as a over n plus b over n plus 1. We've seen this before. It's come up in this class where a and b are constants. So if you multiply through by n plus 1, you get 1 equals what? N plus 1a plus nb. And if you pick values appropriately, if you pick n equal to 0, you'll get a equal 1. And if you pick b n equal to -1, then you'll get b equal -1. And so what happens is this is the same as summing up 1 over n minus 1 over n plus 1. Okay. And that's a telescoping series. And so it's going to give you a finite number. Doesn't even matter what the finite number is, though we can say what it would be. It looks like it's going to be 1/2, right? Or 1/2 for the sum. And then the whole thing will just be 1. Okay, so this thing does converge. And what does that mean? Well, if it converges only if it's transient. So that rules out null recurrent. And we're in the transient state. It's not so important to know what the sum is. It's more important to know that it does sum to a finite quantity, because that's this condition here that we're using. And I think that's what I hinted at the beginning, that it looks like we're going up significantly faster than we're going down. The rates are here. Well, I guess they're all only one difference, but it looks like the push is upward. So this is a transient one. I think I'm out of time. Does that help? I think that does 16, except for maybe the explanation of why what we're using is okay. And I'll save that for another day. Okay. Thanks for hanging with me. I'll see you Wednesday.
See you Wednesday, Professor. Thank you.
Yeah. Let's see. Oh, Zach, you still around? I'm not sure he is. Zachary, are you still here? Okay, I'll catch you another day.